In this lecture, we will be solving a problem for calculating the number of cooling tubes required for a transformer. So the question is, the tank of a 1250 kVA natural oil-cooled transformer has the dimensions length, width and height as 0.65 by 1.55 by 1.85 meter respectively. The full load loss is equal to 13.1 kilowatt. Loss dissipation due to radiation equals 6 watt per meter square degree Celsius. Loss dissipation due to convection equals 6.5 watt per meter square degree Celsius. Improvement in convection due to provision of tubes is equal to 40%. Temperature rise is equal to 40 degrees Celsius. Length of each tube is equal to 1 meter. Diameter of tube is equal to 50 millimeter. So find the number of tubes for this particular transformer. Neglect top and bottom surfaces of the tank as regards the cooling. So we have to calculate the number of cooling tubes required for this transformer. So first of all, let us note down the parameters given. Okay, the tank of a 1250 kVA natural oil-cooled transformer has the dimensions length, width and height as 0.65 by 1.55 by 1.85. So the transformer tank. So it will look somewhat like this. So the length is 0.65 meter. So this will be the length, that is 0.65 meter. Then width is 1.55 meter. So width of the transformer tank is 1.55 meter and height is 1.85 meter. So this will be the height, 1.85 meter. So we have marked the dimensions of the transformer tank. The length, width and height of the transformer tank are given. We have marked those parameters. So now, the full load loss is equal to 13.1 kilowatt. That is, iron loss plus copper loss is equal to 13.1 kilowatt. Now, loss dissipation due to radiation is 6 watt per meter square degree Celsius. So that is a value of lambda given in watt per meter square degree Celsius. So we already know this value. Heat dissipation due to radiation from the transformer tank is 6 watt per meter square degree Celsius. So lambda due to radiation is 6 watt per meter square degree Celsius and lambda convection is 6.5. Now, improvement in convection due to provision of tubes is 40%. Improvement in convection is 40%. So while deriving the equation for calculating the number of tubes, we have taken the improvement in convection as 35%. നമ്മൾ ആ നമ്പർ ഓഫ് ട്യൂബ്സ് കണ്ടുപിടിക്കുന്ന ഡെറിവേഷൻ, വി ഹാവ് എ പർട്ടിക്കുലർ ഇക്വേഷൻ. ആ ഇക്വേഷൻ നമ്മൾ ഡിറൈവ് ചെയ്തപ്പോൾ നമ്മൾ അസ്യൂം ചെയ്തിരുന്നത് ട്യൂബ്സ് പ്രൊവൈഡ് ചെയ്യുന്നത് വഴി കൺവെക്ഷൻ ഓൾറെഡി ഉണ്ടായിരുന്നതിനേക്കാളും 35% ഇംപ്രൂവ് ചെയ്യുമെന്നായിരുന്നു. അങ്ങനെ അസ്യൂം ചെയ്ത് കണ്ടുപിടിച്ച ഇക്വേഷൻ ആണ് നമ്മുടെ കയ്യിലുള്ളത്. ബട്ട് ഹിയർ ദ ഇംപ്രൂവ്മെന്റ് ഇൻ കൺവെക്ഷൻ ഇസ് ഗിവൺ ആസ് 40%. ദാറ്റ് ഇസ് വെരി ഇമ്പോർട്ടന്റ്. സോ വി ഹാവ് ടു അഡ്ജസ്റ്റ് ദ ഇക്വേഷൻ. So we cannot use that equation for number of tubes here. By taking the improvement in convection as 40%, we have to rearrange that equation. We have to adjust that equation accordingly. So keep it there. So next parameter given is the temperature rise. That is theta is equal to 40 degrees Celsius. Then length of each tube. Length of tube is small letter LT, which is equal to 1 meter. Diameter of tube, small letter dt, is equal to 50 mm. Find the number of tubes required for this transformer. We have to calculate the number of tubes and neglect top and bottom surfaces of the tank as regards to cooling. So we don't have to consider the top surface as well as the bottom surface of the tank. So we just have to consider the 4 vertical sides. നമ്മൾ തിയറി പഠിച്ചപ്പോൾ തന്നെ പറഞ്ഞിരുന്നു ട്രാൻസ്ഫോമറിന്റെ ബോട്ടം സർഫസ് കൂളിംഗിൽ ടേക്ക് പാർട്ട് ചെയ്യുന്നില്ല. ബോട്ടം സർഫസിൽ നിന്ന് ഹീറ്റ് ഡിസിപ്പേഷൻ ഒന്നും നടക്കുന്നില്ല എന്ന് നമ്മൾ പറഞ്ഞിരുന്നു. ആൻഡ് ടോപ്പ് സർഫസിന്റെ കേസിൽ 2 കാര്യങ്ങൾ നമ്മൾ പറഞ്ഞു. ഇഫ് ട്രാൻസ്ഫോമർ ഓയിൽ ഇസ് ഇൻ കോണ്ടാക്ട് വിത്ത് ദ ടോപ്പ് കവർ, we have to take full area of the top cover, and if it is not in contact with the top cover, we have to take 1/2 of the area of the top cover. But here it is clearly specified that we can neglect both top as well as the bottom surfaces. So we have to consider only the 4 vertical sides. So while calculating the heat dissipating surface area, that is ST. So while calculating the heat dissipating surface area, we have to consider only the 4 vertical sides. അപ്പോൾ ആ 4 vertical sideന്റെ ഏരിയ ആയിരിക്കും നമ്മുടെ total dissipating surface area of the tank. So how to calculate the area of that 4 vertical sides? So this is the front face. If we are drawing the tank like this, this is the front face. So a similar face will be there at the back side. So this is one side face. So at the back of this side, there will be a similar face will be there. So it will be somewhat like this. So this is one face and this is another face. This face and this face are similar. Similarly, this is the front face, this is the back face. These are similar. So let us calculate the area. So this is our front face. How will we calculate the area? Width of the tank into height of the tank. So width of the tank into height of the tank. And similarly, one similar face is there at the back side. So we have to take 2 into LT into WT plus 2 more faces are there, 2 more vertical sides are there, that is this side and the side at the back of this side, that is this one. So what is the area? Length of the tank into height of the tank, that is 2 into LT into HT. So 4 vertical side ഉണ്ട്. ഈ ഫേസും ഈ സൈഡും ഇതിന്റെ ബാക്കിൽ വരുന്ന സൈഡും സിമിലർ ആണ്. സോ ഈ സൈഡിന്റെ ഏരിയയുടെ ട്വൈസ് എടുത്താൽ മതി നമുക്ക്. അതുപോലെ ഈ സൈഡും അതിന്റെ ബാക്കിൽ വരുന്ന സൈഡും സിമിലർ ആണ്. സോ ഈ സൈഡിന്റെ ഏരിയയുടെ ട്വൈസ് എടുത്താൽ മതി. ഇനി ഈ സൈഡിന്റെ ഏരിയ എങ്ങനെ എടുക്കുന്നത്? ദിസ് പാരാമീറ്റർ ഇൻറ്റു ദിസ് പാരാമീറ്റർ, ദാറ്റ് ഇസ് വിഡ്ത്ത് ഓഫ് ദ ടാങ്ക് ഇൻറ്റു ഹൈറ്റ് ഓഫ് ദ ടാങ്ക്. സോ 2 ഇൻറ്റു വിഡ്ത്ത് ഓഫ് ദ ടാങ്ക് ഇൻറ്റു 2 into width of the tank into, this is not LT, this is HT. Sorry. Okay. For this face, this is width of the tank and this is height of the tank, HT. So, now for this face, this is length of the tank, LT, and this is height of the tank, HT. Okay, LT into HT. So please make that correction here. This is not LT, HT. Okay, so that means this can be simplified as 2 into HT into LT plus WT. So we can calculate the total dissipating surface area like this. The total area of the 4 vertical sides, that is 2 into HT into LT plus WT. So now let us do the rest of the problem. So now let us substitute the values and calculate the heat dissipating surface area of the tank. So ST will be equal to 2 into HT into LT plus WT. It is equal to 2 into height is given as 1.85 into length is 0.65 and width is 1.55. So the answer will be, on substituting the values, the answer will be 8.14 meter square. So this is the value of total heat dissipating surface area of the tank. So now we need to calculate the number of cooling tubes required, but in our equation we have already derived an equation, and in that equation we have considered the improvement in convection as 35%, but here in this question the improvement in convection is given as 40%. So we have to make that correction in the equation. So let us go for deriving the equation again. So how was the derivation? We have considered area of the transformer tank as ST and total area of the tubes, total area of the cooling tubes as X into ST. Then total heat dissipation by the transformer tank, total heat dissipation by the tank. So tank dissipates heat by radiation as well as convection. So total heat dissipation by the tank due to radiation and convection. Equal to, due to radiation the specific heat dissipation is 6 and due to convection it is 6.5. So this is the total specific heat dissipation. That is unit area in heat dissipation. So we are writing the total heat dissipation. That is unit area dissipation into total area. That is into area of the transformer tank. This is the total heat dissipation from the transformer tank due to both radiation as well as convection. That is 12.5 into ST. Now, so we know that the tubes dissipates heat by means of convection. Tube il kuda oil circulate cheyyunnundu. Appo oil variyulla convection variyana tube heat dissipate cheyyunnathu. And it is given in this question that the improvement in convection due to the provision of tubes is 40% more than that without tubes. So let us write total heat dissipation from the tube by convection. Tube dissipates heat by convection. So total heat dissipation from the tube by convection is equal to, convection കാരണം already ഉണ്ടായിരുന്ന heat dissipation എത്രയാണ്? 6.5 watt per meter square degree Celsius. 6.5. And with the provision of tubes, convection improves by 40%. അപ്പോൾ already ഉണ്ടായിരുന്നതിനേക്കാളും 40% കൂടുതലാവുന്നു. That is, it becomes 140%. So 6.5 into 140 divided by 100. This will be the new specific heat dissipation. But tube provide ചെയ്ത് കഴിയുമ്പോഴുള്ള specific heat dissipation ആണിത്. And we are writing the equation for total heat dissipation. So that will be specific heat dissipation into total area of the cooling tubes. That is into X into ST. So this will be 6.5 into 1.40 will be 9.1. So 9.1 into X into ST. So this is the total heat dissipation from the tubes. Okay. So now total heat dissipation from tank and tubes equal to ടാങ്കും ട്യൂബും രണ്ടും കൂടി ചേർന്നുള്ള total heat dissipation. That will be equal to 12.5 st plus 9.1 xst. Which is st into 12.5 plus 9.1 x. So now let us write the equation for temperature rise. So we have temperature rise theta is equal to Q divided by S lambda. That is total loss divided by total heat dissipation. Total loss is Pi plus Pc, iron loss plus copper loss, divided by lambda is the specific heat dissipation from unit area, and S is the total area of the heat dissipating surface. So this will give, S lambda will give the total heat dissipation. So we have calculated the total heat dissipation from the tank and tubes, and it is 12.5 plus 9.1 x into St. So rearrange the equation and find out the value of x. So x will be, this equation can be rearranged as 12.5 plus 9.1 x will be equal to Pi plus Pc divided by theta into St. Or we can write 9.1 x as this term minus 12.5. Okay, now what's the value of x? This term divided by 9.1. That is, x will be equal to 1 divided by 9.1 into this term. And we need the total area of the cooling tube. That is, x into St. So that will be total area of the tubes. X into St is equal to this term into St. So that will be x into St, that will become 1 divided by 9.1 into Pi plus Pc divided by theta into, so we have to multiply x by St. So this St gets cancelled, divided by theta minus 12.5 into St. So this is the total area of the cooling tubes. So we got the total area of cooling tubes like this. And if we know the area of one tubes, then by dividing this total area by area of one tube, we will get the number of tubes required. That is, number of tubes will be equal to total tube area divided by area of one tube. Okay, so now tubes are cylindrical in shape, so area of the tube will be similar to surface area of a cylinder. So let LT be the length of the tube and DT be the diameter of one tube. Then area of one tube can be written as is equal to pi dt LT. Okay, then number of tubes will be equal to 1 divided by 9.1 into pi dt LT into Pi plus Pc divided by theta minus 12.5 into St. So this is the expression for calculating the number of tubes. So now by substituting the given parameters, we will get the number of required tubes. That is, n is equal to 1 divided by 9.1 into pi into dt. diameter of one tube is given as 50 mm. So we have to convert mm into meters. So 50 into 10 raised to minus 3 into length of one tube is given as 1 meter into Pi plus Pc. The total loss is given as 13.1 kilowatt. Convert kilowatts into watts. So 13.1 into 10 raised to 3 divided by theta. Temperature rise is given as 40 minus 12.5 into St. So we have calculated the total surface area, heat dissipating surface area of the tank, and we have got it as 8.14 meters square. Okay. Now, if we calculate this value, we'll get the number of tubes as 158. So if we are not getting an integer, we have to round off the value to the nearest integer. Okay, here the answer will be 158. So we got the value for number of tubes required. Now, as we have done in the previous problem, we have to find the arrangement of tubes also. So you can do it by yourselves. How to arrange these tubes on the 4 vertical sides of the transformer.